and welcome to today's webinar by XP Solutions, Hydrology 101, a modelling demonstration. My name is Gavin Fields and I'm a Senior Water Resources Engineer here at XP Solutions. Today's webinar is a follow-on from one of our recent webinars, Hydrology 101, and has been prepared in response to the large number of attendees who are keen to see some practical applications inside the software pursuant to that previous webinar. Today is part of our XP Live educational program, and the webinars are recorded and will be available on our website. Today will be a reasonably short webinar, hopefully. I don't want to take up too much time. But as an agenda, we'll have a brief introduction, again a follow-on from the previous webinar, discuss the hydrology inside our main tool, XP Swim, and look at the data types between historic and design storms, some routing methods, and have a review a lot of the time inside the software for 1D and 2D rainfall. And at the end, of course, we'll try and spend as much time as required to answer any questions that any of you have over the course of today's session. So as a quick introduction, XP Swim is a engineering tool that models stormwater, wastewater, and flooding. It is used across the world and is a graphical user interface with two key analytical engines, one being a 1D engine and a 2D engine, and we produce a large variety of results types for modelling, interpretation, presentation and approval for development activities. So for today, again this is a slide we had in our previous webinar, but why is hydrology important? Hydrology is critical for planning, for urban development, residential areas, encroachment points, to understand the impacts associated with the land use changes and the subsequent risks associated with flooding. It is also important for agriculture, where in an ever-increasing perception of climate change, the demands for our water resources become ever more important. As a very quick overview of hydrology, it is the summation of rainfall minus losses to create runoff. Now precipitation and the inflows to our hydrology will generally come in the form of rainfall, but can also be a result of snowmelt and also groundwater base flow discharges. Losses from our models or in the real world are in the form of evaporation and transpiration from plants, infiltration into groundwater, and also surface storage or depression storage. We then try and convert that runoff into hydrographs as shown in the diagram at the bottom, where we subtract our infiltration from our inflow rainfall patterns or historical rainfall data to derive a hydrograph and assess peak flows, total volumes, and then at a later stage, which will be part of a future webinar series on hydraulics, convert that to discharge and observe where that flow moves through to. Of course, the first part of hydrology is to understand our catchments. Again, this is taken from our previous slides showing a road along a ridge that is called the interfluve, and this is the principal component to start your hydrology assessment, understanding your topography. Catchments can vary in size from this small park or to any of the development areas in this particular photo, but can also increase to very large-scale basins, such as the Murray-Darling Basin, which covers approximately a seventh of Australia as a singular catchment area. To support us in assessing our catchments, we do need to obtain topographic information, whether that be in the form of detailed survey or historic elevation maps, but that's the first point of contact in preparing your hydrologic model. Moving forward quickly, we then have the choice of providing a modelling package such as XP-Swim with design storms or historic rainfall data from your hydrological department. Key parameters that our software rely upon are quickly summarised here. Obviously rainfall, catchment areas, I beg your pardon, based on those topographic features is number one. The second point from the data entry perspective in our software is the fraction impervious, which is a function of its land use characteristic, its catchment slope, the roughness of the catchment, and at times the length or width of the catchment may be important depending on which method of analysis you're interested in. Inside the software there are many hydrologic methods available to our users. The EPA swim runoff method, my apologies, is a dominant method in America. Here in Australia the Lawrenson's method is very favoured, and across the American and Asian regions the Soil Conservation Service methods would probably be the number 2 or 3 method out of most of our user base. And of course there are other regional methods that have been prepared for specific areas. And so what do we want to produce? Obviously we want to understand our peak flows, prepare graphs similar to these at the bottom of the screen to understand our historic rainfall or design storms. At this point I'll jump over into the software and we can have a look at the practical applications inside Suite. So this is a simple model that is available to all of our users or potential users. If you are willing to contact us here at XP Solutions, we can provide evaluation versions or trial versions of the software, and these data sets are included for your use following this session. But in this example, I just have a number of nodes and some catchment areas that have been already drawn into the software. And we can link catchment areas that are either been drawn manually, which I could do like so to continue to manipulate this. And I can quickly add an additional catchment as required. We can link these catchments to our nodes inside our software, and we can derive additional information from these polygons very rapidly. Once you've done this for the entire catchment, we can use tools within the software to calculate catchment areas, and it will give us a quick report on the elements that I've changed to show that up. And now when I click into these elements, I can see that I have the catchment areas have been applied to the nodes. We can see here that we still need to obtain additional information beyond these elements. If we have a GIS database in the background, I can load catchment information, and I have a GIS shapefile. Now that I've linked this shapefile into the software, I can now actually, if I hide these catchments, I can see that the catchments are available from this GIS file as well, these black polygons. I've right-clicked on this layer, and then this has brought up this dialog box where I can select attributes from the shapefile and then apply them to core components of the software. Part of the cookie cutting feature of this element is that if you have multiple polygons with land use information that may include fraction impervious components, then we can do an area weighted method to derive a final fraction impervious, for example. So if a component of the catchment was used for open space and then residential adjacent, you may wish to get a cumulative fraction impervious that may be as low as 20 or 30%, factoring in even the urban development area. You can also do area weighted or dominant, which is simply the largest polygon over the top as a method of applying information. I'm just going to go with the area weighted, even though I've only got one, just to demonstrate that can work. And I can add elements such as slope, and I'll just maintain width, probably the last one that I'll do here. If I hit import here, the software gives me a text file summary of what has been modified, and I can review that to confirm that the changes are acceptable. But I can also do that inside the software. By double-clicking on node D, for example, I can see that I have a fraction impervious has been brought in from this GIS file of 12%. A width value has been applied. This may be specific to a particular hydrology method, and catchment slope as a percentage of 3.2% has been brought in from this GIS file. So that's a very rapid way of utilising existing data sets if you have them available to yourself. If I go into the catchment, I would then need to tell the software which hydrology method I wish to use. In this example, I'm just going to show the SCS hydrology. And SCS hydrology relies on curve numbers for its loss method, and also a time of concentration. The time of concentration could be roughly identified based on the length of the catchment, of course, or we're using other calculation methods. But just for today's example, I'm going to assume a 15-minute time of concentration. And because I have such a low fraction impervious, the curve number will similarly be low, and I'm going to apply a curve number of 35. The method also has the ability to have an initial loss or initial abstraction, and I'm going to apply a 10 millimeter initial loss, again because of the pervious nature of this catchment. I then have to select my rainfall, and I can again use one of the Soil Conservation Service patterns. I'm just going to select that type 2 pattern and edit it, and I'll show you what that pattern looks like inside the software. And if I hit graph, I can see that is the temporal shape of this pattern. We can see here though that the rainfall intensity that's currently being applied cumulatively adds up to only 1 millimeter, and that's a function of this multiplier in the dialog box below. So if I go back to that point, and if I were to apply a 24-hour, say 100-year depth or 1% AEP rainfall value, I might expect that to be in excess of 350 millimeters for where I am here in Brisbane, in Queensland, Australia. And so now if I regraph that, I can see that for the peak of this event, I might expect rainfall intensities that nearly approach 500 millimeters per hour. I'm going to hit OK on these elements, select that rainfall, and hit OK. This information would then need to be transposed to the other nodes inside the model. But just for today's example, I'm going to run just that one particular element. I'm just going to turn these elements off before I run the software. But before I do run, even hydrology also needs to know the time that it occurs. We do this under our project job control. If I go into my time control settings, I'm going to run the storm. I'll tell it, because it's a design event, that the time that we set here will be when the rainfall occurs, and I'm going to run it for 24 hours. I'm just going to solve this particular model. Obviously missed a node there, but that's okay. And I'm going to review this particular catchment's results. And so from this 6 odd hectare catchment, I'm generating a peak discharge from this particular pattern of about 3.5 cubic metres per second. And so that's a very simple way of getting our hydrology results using our tool, only relying upon the core information being catchment area, fraction impervious, which wasn't actually applied to the SCS method, so that number wasn't particularly important, but also the catchment slope. The other hydrology methods available to us, which also include, as described before, Lawrenson's method here in Australia. Lawrenson's method has enough information to calculate the B value, which is the critical parameter for the storage equation. That's important. There's enough information inside the software to derive that automatically, and we can then select any rainfall. But in that method, we would also need to define a loss model, because the SCS curve method has its own internal loss method. One of the common loss methods is an initial continuing loss method, very popular here in Australia. And under the uniform loss method, we can set any value for an initial loss, whether that be 15 or 10, and then a continuing loss, which may be in the order of 2.5 millimetres per hour, or other as applicable to your catchment. Or conversely, you could go for a proportional loss, which is a proportional value relative to the rainfall intensity. Different methods inside the software also rely on potentially depression storage, catchment roughness, which Lawrenson method does, and also groundwater detention. And these need to be specific for each particular method that the user wants to apply. And once selected, that would then be applied, and of course we could rerun the analysis and generate a different hydrograph. That's a quick summary of one-dimensional hydrology inside the software. However, the other method that is becoming popular is direct rainfall. So I have another model in the background. I can click over to it. And this is a catchment area here in Queensland. There's two major roadways crossing each other, and a small pocket of residential development and a lot of rural area. Again, starting from the top of this session, we need to look at topography. And so in this instance, we brought the surface terrain into the software. And from this, we could manually derive catchments. Like so. And these could be linked into respective drainage points. Or we could and go through the same process we just did a moment ago. Alternatively, we could apply what we call a rainfall flow area. And this is a simple catchment polygon that covers the entire area. And we have applied to this, by editing its data, a particular storm event to that entire polygon. This model takes a bit more time to run, so I've already solved this particular model to see how the hydrology applies, but also looking at it in 2D results. And when we look at the maximum water depth from this model, we can see that the entire catchment area is total area is covered in water, rather than having point hydrology. But that's a very simple way of simply defining one total area and applying our rainfall to terrain instead of accumulating it at a 1D perspective. That functionally completes today's webinar. We really appreciate your time in attendance today. Thank you again for your time.